So down here at the bottom of page 1, we're in 2.1, page 1b here. The next three examples, the header here says these are not linear equations. And so our question will be, why not? What rule are they breaking? So at the top, in the middle of your notes page, kind of where I'm pointing here with the pen, is the checklist we just went through. X is a single variable. There's no other variables involved at this point, okay? As we get to chapter 4, we'll replace these numbers hanging out here on the other side of the equal sign with a y. But for right now, you just have an x involved. There's an equal sign, and then the numbers that are in front of those, that are in those positions, the ax plus b equals c. There's something being multiplied on the x, there's something added or subtracted from the x, and then it's equal to some value over here. This is the standard form of that equation. So there's an equal sign. A, b, and c are real numbers. The exponent of the variable is just plain old 1, and x isn't trapped anywhere. There's no radical over the x, there's no absolute value, that kind of thing. Okay. Now, as we move on, the equations are going to they're going to start needing to be simplified. This is after you've simplified. It meets all these requirements. Okay, and that'll make more sense as we see some more examples. But let's hit this real quick. Why aren't these? So as you look across here, you've got an x, you've got an equal sign, you've got numbers in front here, you've got a 1, a minus 15, or that can be considered a plus, a negative 15, you've got the 20. They're all real numbers here, but the catch is that the variable to x is not equal to 1. So the exponent of the variable is not equal to 1. So the exponent doesn't equal 1, so that's why not. So no, it's not a linear equation. Let's look at number 6 here. 15 over x equals 20. So this one just looks really different. What are we really looking at here? Now this is some preview information. We'll deal with this more specifically in Math 65, but for now, when you see an x on the bottom, what you're looking of a fraction, what you're looking at is 1 over x, and that's being multiplied by 15. So in one sense, we've got 15 times 1 over x plus 0 equals 20. So we've got an x, we've got an a value, a b value, and a c value here. This is a is what's being multiplied by x. But what's happening here is the problem is the fact that x is in the bottom of the fraction. It's the denominator. And what we'll learn in Math 65 is that 1 over x means that the exponent of x is negative 1. Okay, we just started talking about exponents. I hinted at the fact in 1.8 that once we know exponents, then we can start looking at, well, what would x to the 0 equal? And that's really a Math 65 topic, but I invited anybody who wanted to kind of check that out. You know, talk with me, and there's some resources online too to kind of look at that. But then if an exponent could be 0, then it could also be a negative number. And what happens with the negative exponents is it flips it. It puts the variable on the bottom. So, and that's not what we're learning right now. What we're trying to grab right now is whether or not these are linear equations. So with the negative exponent, once again, it breaks that rule. Here the exponent is not equal to 1. Okay, it's a negative 1, and that's completely different. So when you see x in the bottom of a fraction, you do not have a linear equation situation. So this is no, not a linear equation. Which shouldn't surprise you in this list, because I said these are not linear equations. Why not? So all of these are not. And here right away we see that x is trapped inside the absolute value. So even though it has an a value, it has a 1 being multiplied by the x, it has plus a b value here of 5, it has a c value of 8. Those are all real numbers. It has an equal sign, has a variable, the variable's exponent is 1. The problem is that what it doesn't qualify is the fact that the x is trapped inside of absolute values. So x is in the absolute value. And what that does is it causes it not to be the linear relationship. And that will make more sense after we get through chapter 4. But for now, x is in the absolute value, and that is enough for us to say, no, it's not a linear equation. Okay. So what if it looked like this on number 8? Radical 3x plus pi equals 0.6 with a bar. And let me just clarify here that radical 3 is the number in front of the x. So it's like radical 3 times x plus pi equals 0.6 with a bar. Okay. So a little bit testing here our knowledge of numbers and the categories they're in. When you look at the requirements to be a linear equation, we're looking for something of the form ax plus b equals c, or that it can be rearranged to that form. We're looking to see that those a, b, and c values are real. We're looking to see that x has only an exponent of 1 and there's no other variable involved. And then we make sure that x is not trapped anywhere. So it isn't trapped. It's outside the radical. This is multiplication. Be very, very clear about that. So it is just a exponent of 1, so that's fine. It does have the equal sign. The big question it comes down to is, are a, b, and c real numbers? And in this case, they sure are. Real numbers include everything. They include the rationals, which would be the repeating decimal right here in 0.6 bar. They include the irrationals, which would be like pi and radical 3. So yes, they are. And so, yes, they are real numbers, and so yes, it's a linear equation. So the instructions that I highlighted here for you in the book, they say identify the linear equations in one variable. What they're saying in fancy, fancy terms is you decide yes or no if it's a linear equation or not. So just like we did on these examples. And then the next set of things that they're going to have you do. So this is just the beginning, just getting exposure. You're not solving or anything at the beginning. You're just saying yes or no, it's a linear equation or not. Then we'll move on to solving, and that's what the instructions for the next set of problems will be. Solve each equation, use the addition property of equality. So on page 2, we're going to hit some examples, and we're going to be using the addition property of equality. The book takes you through what an expanding version of solving equations. So they start with just what many people refer to as a one-step equation. Then once you get comfortable with that, the book moves you on to two-step equations. Then when it gets you comfortable with that, it moves you on to equations that have to be rearranged before you can solve it as if it were a two-step or a one-step. What I've observed over the years is that many of us then think there's all different kinds of rules for how to solve equations because it seems like the rules keep changing as you go through. For some people, it's a fine way to learn. It's just kind of building on smaller building blocks first and then getting bigger into bigger concepts. So the way I'm going to teach it over the next couple of sections is I'm going to give you all the steps from the beginning, and it'll be a checklist, and sometimes we won't have to do we won't have to do some of the steps in the checklist because it'll be a simpler version of the equation. But by the time we get to the sections where the equations are a little more complicated and involved and require all these steps, we'll have them memorized and ready to go because we've been practicing them all along. So here's what they're going to introduce in the book at this particular time is the addition property of equality. And what it says then is that if you have something that's already equal to each other, A equals B, then you can add the same thing to both sides and you still have an equal statement. So if you add the same thing to both sides, whether it be a number, a variable, it's still equal. Because we can't change things as we go through mathematics. If it's given to us as an equal or equivalent statement, an equation, we can't change that. We can't, if we say something's in balance, we can't put something on one side or the other of the balance and then expect it to still be in balance. We have to put the same amount on those scales and it'll keep it in balance. So same thing with an equation. Alright, so that's kind of the preview of where we're headed on the rest of this section. So we'll see you on page 2.